Alright guys, so I promised I would cover these last notes that we didn't get to in the acute cardiorespiratory response to exercise. So I'm going to do that, and then as well I'm going to spend a little time talking about the TBL activity slides that we didn't get to today, because I think some of that will be helpful for your understanding for the gallery walks as well as for the exam next week. So first off, we didn't really get to this slide about talking about the different things that affect afterload. Okay, and so again, afterload is going to be the amount of pressure that the heart has to overcome to get blood out. Okay, so there's always pressure on the other side of that aortic valve, and the job of the left ventricle is to create enough pressure to overcome that pressure on the other side and open up that aortic valve and push blood out. Okay, so it's only going to be open for the amount of time that the pressure in the left ventricle is greater than the pressure in the aorta. As soon as that pressure gets high enough to be greater, it's going to open up the valve, blood's going to be going out, 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 but then as soon as that pressure dies down to where the pressure in the aorta is higher, blood's immediately going to start backflowing towards the heart, and that's going to close the aortic valve, and your stroke volume is done for that stroke. Okay, so there's some different things that can affect this. Obviously, high blood pressure does, because that's what we're talking about here, is increasing blood pressure to increase afterload. Okay, and so some things that also will increase this blood pressure are atherosclerosis, so stiffening of those arteries, and closing in on the arteries by making the walls thicker. We'll talk a lot more about that towards the end of the class. Aortic stenosis, so just same thing, but make the aorta actually getting smaller because of plaque buildup. Hand grip maneuver, meaning that you're kind of squeezing down, bearing down a little bit. That can increase pressure in the vascular system. And then with exercise, this one is kind of interesting because the book talks about this, and it says that total peripheral resistance is decreased with exercise, and this allows us to have a greater stroke volume. And I think that's a little bit misleading, because if you've ever measured an exercise blood pressure, then you know that blood pressure during exercise is much, much higher than it is during rest. Okay, it's very typical for systolic blood pressure to be up to 160, 180 during exercise. And diastolic pressure doesn't change much. Diastolic pressure might even decrease a tiny bit, might go from 80 to 75, something like that, but it doesn't change much. So if you do the MAP equation, right, 2/3 times diastolic pressure, 1/3 times systolic pressure, if you take that 160 times 1/3 and maybe 75 times 2/3, add those up, that's going to be a lot more than 120 times 1/3 and 80 times 2/3. Okay, so blood pressure is still higher during exercise, but the point that the book is trying to make, which I think it does in a confusing way, is that because of the vasodilation that we have in muscle, that makes blood pressure lower and total peripheral resistance lower than it would have been if we didn't have that vasodilation, because of all the vasoconstriction everywhere else in the body, because of all the sympathetic nervous system activity. We have a lot higher blood pressure, but since we have some vasodilation, that does help a little bit, and that does decrease afterload some. But afterload during exercise is still much higher than afterload during rest. So in general, this actually doesn't help us get more stroke volume during exercise. It actually is fighting against us a little bit. So we have to rely on the other two factors, contractility and preload to increase stroke volume. Okay, so contractility is the last factor here that we need to talk about with increasing stroke volume. And again, contractility is the strength of the contraction, the force of contraction. Okay, and this is determined primarily by the sympathetic nervous system activity. Okay, so force of contraction, sympathetic nervous system activity, and the way that we measure this is ejection fraction. Okay, so the better the ejection fraction, then the greater the contractility, because more of the blood got out, meaning that the heart squeezed down harder. Okay, so I did want to give you an example of how to calculate ejection fraction, because I kind of just mentioned that today in class, but I didn't actually completely work it through with you. And so the way we do this again is we do stroke volume divided by end diastolic volume. So what we started with, the full amount of blood that was in the heart, that's going to be what we divide by, but what we want to put on as a numerator is the amount of blood that came out. Okay, so of that amount of blood that we started with, what percent came out, and that's really the ejection fraction. So you get, so in this case with the resting, 100 mLs was the stroke volume. We started with 150, so we divide those. That's going to be 0.666, times that by 100 to turn this into a percentage. And this shows this cross-country skier is resting. If we're using these numbers from the TBL activity today, his resting ejection fraction was about 66%, which would be very high, which would be good, which would be believable with this type of person. But then maximally, end-diastolic volume was 220, stroke volume was 200. So you have 200 divided by 220, that's going to be 0.909 times that by 100, 91%. Okay, so again, when we talk about all those factors that are changing cardiac output, we've got, changing stroke volume, really. Again, we've got a lot more blood to start, so venous return went up quite a bit. That's at end diastolic volume increasing. We talked about all the ways that venous return increases. And then number two, of that, since we got a lot more blood in, but it's even more impressive now that of that blood that we got in there, it's not that we got the same percentage out, we got a way higher percentage out, even though we had so much more in. So that's all about the contractility and the sympathetic nervous system activity that you see. Okay, and so this is just looking at those same Frank-Starling curves, looking at stroke volume here on the y-axis, preload on the x-axis. And so when we have low sympathetic nervous system activity, the curve might be down here. But if we increase sympathetic nervous system activity, then we are increasing contractility. And so for that exact same amount of preload, we have a lot more stroke volume, right? Just meaning that ejection fraction went up. We started with the same amount, but we have a lower end systolic volume, right? Smaller end systolic volume meaning we have less in there afterwards, so it means we got more out, so higher ejection fraction. And same thing here with even higher contractility, even higher sympathetic nervous system activity. Okay, again, this is kind of looking at the same thing, except this is just showing cardiac output, okay? And this is looking at sympathetic stimulation up here. We have an increase in contractility and heart rate, so it's going to drastically increase cardiac output. Down here, if we have parasympathetic stimulation, we decrease heart rate, and then we don't have that same stimulation to increase contractility, and so everything's going to be down here, just showing how the cardiac output kind of gets in there. Okay, so one of the slides that we didn't get to today was this, and this is talking about the AVO2 difference. So again, resting AVO2 difference might be somewhere around, and if you look at this right here, you can see this is venous content, this is arterial content, okay? And so we're maybe around 18 to 12, so that's maybe a 5 to 6 ml difference, okay? And then maximal, we're going here from, again, about 18 down to probably about 4, so maybe about 14, maybe that's 3, so maybe about 15. So that's pretty typical that we would see going from 5, an AVO difference of 5 mLs at rest, maybe up to 15 or 16 at maximal exercise. Okay, so this is what we didn't get to. This is very important. The question in this, your slides address this for the TBL day, but we didn't get to talk about it. The factors that are involved in increasing this AVO2 difference. As we just saw on that slide, there's really no change in the amount of oxygen in the blood on the arterial side, but there's a big drop in the amount of blood left over amount of oxygen left over in the blood in the veins. So what that means is we extracted more oxygen. Okay, so how do we extract more oxygen? Okay, there's a few primary ways. Number one is we put more blood in capillaries at any given time. If blood's in capillaries, then it has the ability, the body has the ability to extract oxygen out of it. Okay, and so what this means is we open up more capillary beds. Capillary beds can be controlled by vasoconstriction, by these little sphincters that block the blood from going in there. Okay, and if blood's not in a capillary, oxygen can't come out. And that's just the bottom line. That's the only place diffusion happens is in capillaries. And so the more capillary beds we open up, the more extraction we get. So the more active muscle mass we have, the more extraction we're going to get, right? So that's number one. Number two is, what's actually using that oxygen, right? Our mitochondria are using that oxygen. So the more mitochondria we have active, the more oxidative system we're using, the more taxed all of those muscles are oxidatively, then the more we're going to be pulling blood out of the system. That can also be said for the training effect of just having more mitochondria and muscle. That's going to cause us to extract more oxygen. So those are the two main factors there, that we have more blood in capillaries and we're activating more mitochondrial mass, and that's going to be pulling more oxygen out of the blood. Okay. Okay, and so the point of this slide is really to try to put all these things together into one. And so the Fick equation we've been talking about, the point of the Fick equation is to measure oxygen uptake or oxygen consumption, right? And so we that's what we do, but we've really just been talking about each of the different components separately. So what I want to do is take the examples we had from that cross-country skier, and then also for cardiac output at least, and then for the AVO2 difference, we'll just use the AVO2 difference that we saw in the book and the chart that figure that I showed. And so cardiac output of that skier was 36 liters per minute, and the AVO2 difference is 15 mLs of oxygen for every 100 milliliters of blood. These are both the maximal values. So if all we need to do for the Fick equation is times these two things together, but we have them in separate units. So the first thing we have to do is convert this 36 liters per minute to milliliters per minute first. So we just take 36 times it by 1,000. So we've got 36,000 milliliters of O2. Sorry, not of O2, it says O2 there. 36,000 milliliters per minute of blood is the cardiac output. Okay, so then we're going to times those two things together. So we've got 36,000 milliliters of blood per minute times 15 milliliters of blood, 15 milliliters of oxygen per 100 milliliters of blood. Okay, so what we'll do is we will, so we'll times 36,000 by 15. Okay, and then we'll just divide that by 100. Okay, what that ends up giving you is 5.4 liters per minute. And so what it's actually going to give you is 5,400, right? And then you're going to take that 5,400 and divide it by 1,000 to go from milliliters to liters. Okay, so this person's absolute VO2 max is 5.4. You can go ahead and do the math. So again, first thing you do is 36,000 times 15, and you take that number divided by this 100 down here. That'll give you 5,400 milliliters per minute as the VO2 max. Divide that by 1,000 so we can get VO2 max into liters per minute. But to put that more into something that makes sense to us, we can put it into mLs per kg per minute. So to do that, first of all, we need to put it back into milliliters. Okay, so we take that 5.4 times it by 1,000, and let's say this is an 80 kilogram person. So we divide this 5,400 by 80 kilograms, and we get a VO2 max of 67.5 mLs per kg per minute, which would be a believable VO2 max for someone who's a highly trained endurance athlete like this person would be. Okay, so work through those calculations, make sure you get that. Okay, then last slide here that we didn't get to is talking about the ventilatory threshold. And this is important because this kind of, again, brings together some other concepts with the with some of the chemicals involved in the with the chemoreceptors and driving ventilation. So the things that cause this, we know that CO2 is the main driver of breathing. Okay, and what I like about this graph is it shows the alignment of lactate threshold, which these are lactate levels in yellow, and ventilation levels in red, and they both ventilation's going up linearly, and all of a sudden it breaks off of that linear path and shoots up. Okay, that happens right somewhat close to the same time that lactate levels shoot up. Okay, so again, this goes back to that extra CO2 that's coming from the bicarbonate buffering system, because all of a sudden we're making a lot more lactate. We're making more lactate than we can deal with, so we have a buildup of lactate as well as a buildup of CO2. If we have a buildup of CO2 and hydrogen, those things are both driving ventilation faster and deeper. And so instead of having this nice linear increase in ventilation as oxygen goes up, we get a big rise as soon as we start building up lactate, right? And so the ventilation threshold is tightly linked to the lactate threshold because of that extra CO2 that comes from the buffering system that leads to more breathing. Okay, so that's the chemical factors, right? But the energy systems are related to this too, right? Because we in order to improve the ventilatory threshold, the ways we can do that are, one, we could improve our buffering capacity, but two, we could make sure we're using our oxidative system longer, and we don't have to rely on anaerobic glycolysis as early and as much. If we did that, we wouldn't be making as much lactate. This lactate threshold could move out, right? And we wouldn't be making as much, and so this ventilation threshold could also move out because we wouldn't have that buildup of CO2 as early. Okay, and so So that's very important to note that the energy system are related to this. That this means we're using, to have this breaking point, it means we're using a lot of anaerobic metabolism and not as much aerobic. If we have a much stronger oxidative metabolism system, meaning much stronger, more powerful mitochondria, more oxidative fibers, then this is going to move out, right? This is going to occur at a higher oxygen uptake because our aerobic system is handling the demand for longer. Okay, and so again, the factors that drive ventilation are CO2 levels, hydrogen ion levels, but then all kinds of other things that are integrated in, like that one integrated response figure in your book showed. But the main ones I'm concerned with definitely are the CO2 and hydrogen. Okay, I think that wraps it up, guys.